Many of you know the formula for the sum of the first n numbers. That's 1 plus 2 plus 3 all the way up to n. This is sometimes called a triangle number. It has a nice closed form. It's n times n plus 1 over 2, or as I like to write it, n plus 1 choose 2. In this video, we're going to look at a slightly different sum. That is the sum of the first n squares. So 1 squared plus 2 squared plus 3 squared all the way up to n squared. And we're going to find a closed form. In fact, we're going to find several different closed form solutions for this summation that are all derived from manipulating something called polycubes. The polycubes are collections of cubes that are glued together along their faces. These are flat polycubes because they're representing the squares. If we stack these squares carefully, we make a nice little pyramid. So really, the sum of squares gives us a pyramid, and so our goal is to find a closed form for the volume of a pyramid. Now, if I have 3 of these pyramids, they fit together quite nicely, and they almost make a cube. The only difference between this shape and an actual cube is that there seems to be an extra triangle on top and an extra square in the back. So if we break this apart, we get that 3 pyramids is made up of a cube, a square, and a triangle. That gives us our first closed form. The pyramid is the sum of squares, which is written as a cube plus a square plus a triangle, or perhaps more commonly in this form. I can take that cube apart, and I'll get 3 pieces which are almost pyramids, one of which is a pyramid, one is a smaller pyramid, and one is missing a triangle, and I can reassemble them and get back to my 3 pyramids. Let's consider a related problem. Instead of adding up squares, let's take the sum of triangles. This collection of discrete triangles, if we again stack them up, what we'll get is a discrete analog of a tetrahedron. Now, the closed form for a discrete tetrahedron is much easier than the sum of squares. So again, remember the triangle is n plus 1 choose 2. The tetrahedron of size n is going to be n plus 2 choose 3, which follows directly from Pascal's identity and also generalizes directly to d dimensions. Going back to our pyramid, we see a pyramid decomposes into 2 tetrahedra, one unit smaller than the other. So this gives us another distinct closed form for the pyramid. It's the sum of squares now written as n plus 2 choose 3 plus n plus 1 choose 3. Let's go back to having 3 pyramids. If I take one of these pyramids and I split it into 2 tetrahedra, like we did before, and I replace one of those tetrahedra with its mirror image, so the total volume stays the same, I can do a little adjustment using my handy hot glue gun here and get a new shape which has the same volume as a pyramid. Now, I have three pyramids worth of volume, and if I can figure out how to rearrange them, what we'll get is a new shape. Let's see, somehow, yes, good. This one goes over here, and what we get is a triangular prism of height 2n plus 1. That gives us another closed form where we write 3 pyramids as 2n plus 1 times a triangle, and so the sum of squares is 1/3 of 2n plus 1 times a triangle. Let's take a look at what happens if we take 4 standard pyramids and we put them together to make one shorter pyramid. Now, this is not a standard pyramid because you'll notice the squares at each level are only the squares with an even side length. I can make this same shape by piling up those even side length squares. In this case, I've made them out of triangles. And what we'll be able to do is separate out now this pyramid into two halves. Now each of these two halves is almost a tetrahedron, except unlike the tetrahedron, which was a sum of all the triangles, I have on the left the triangle numbers for n even, and on the right the triangle numbers for n odd. So if I alternate those triangles, taking them apart, stacking them in order, they come together to make a larger tetrahedron. This new tetrahedron is twice the height of the original pyramid. This gives us a new closed form. It says that pyramid of size n is going to be 1/4 a tetrahedron of size 2n, or can be written out as shown here. Let's see if we can apply some of these same ideas to look at the sum of cubes. Here I have 6 tetrahedra, and if I rearrange them, what I will see is that there is one tetrahedron of size n. There are 4 of them that are one smaller. We'll call those n minus 1. And there's one that's one smaller than those. We'll call that n minus 2. If I take these 6 tetrahedra, I can arrange 3 of them into a triangular prism, and I can arrange the other 3 into another triangular prism, slightly smaller, and these two come together to make a cube. This is perhaps not surprising. We know a regular cube can be decomposed into 6 tetrahedra. This just means the same is true in the discrete case, but it also gives us a new closed form for the sum of cubes, because if I write a cube this way, the sum of those cubes is going to be the sum of the tetrahedra, but those sums of tetrahedra are sums of 4 simplices. If you want to 3D print your own polycubes, you can download the code at GitHub. It's released open source, simple Python library. It works with OpenSCAD. Thanks for watching.